All right. I think we got just about everybody. I don't see Ben. Who else are we missing? We'll see if he makes it in. Here we are, Thursday. It's kind of like Friday on this schedule. So tomorrow you guys don't have any class, but we are available for office hours. So keep that in mind. That's for all of your teachers. So if you are having any trouble with any of your classes, you can certainly get onto our office hours and we'll be happy to help you with any of that. So I don't know about you, but I think I'm getting this down and it's working really well. So I think it's been good. All right, so as always, we will begin with a prayer. And Matthew, can I volunteer you to be our leader today?
Sure.
In our prayer, you may choose whatever prayer you'd like.
In the name of the Father, Son, Holy Spirit, and our Father, who art in heaven, hallowed be thy name. Thy kingdom come, thy will be done on earth as it is in heaven. Give us this day our daily bread, and forgive us our trespasses. We forgive those who trespass against us. Lead us not into temptation, but deliver us from evil. Amen. In the name of the Father.
Thank you. All right, well, happy Thursday. Listen to this one today, gentlemen. It's a good one. So April 2nd. Hopefully you guys had a good April Fool's Day yesterday. Today's mustard seed. Time directs, heals, teaches, and leads hearts to love. Be patient with yourself and with others. Be patient with God. That one was good for me this morning. So we're all requiring lots of patience now, aren't we? All right, so as we move on today I do have some notes to be giving you. What you will see written up here, there is a document online. Hopefully Blackbaud will stay functioning correctly all weekend. And you will find that document called Conceptual Questions on Momentum. So yesterday's or Tuesday's homework was just to read what I needed you to take a look at there. And today we're actually going to answer some questions to go with momentum. So I want to reiterate what you read, kind of talk through it, show you some examples of things, and hopefully you'll be able to answer those questions. Because we're not in class and I don't have the warm-up sheets where that's how I graded your work, I am going to ask that you just take a picture and scan your homework into Blackbaud. It doesn't have to be necessarily correct, so I'll use the same standards as I had for homework in the past, which is, a good attempt on it, a valid attempt, and that's, in my opinion, what's considered a valid attempt. But make it a good attempt, and it doesn't necessarily right or wrong. So it is more of a participation grade that you are getting it done and putting good effort into it. Okay? So before we begin, does anybody have any particular questions? All good? You all tired today?
I have a question.
Yes, Hector.
So are we gonna just be taking notes today?
Today is pretty much all notes. Yep, on the whiteboard. So what I'm going to ask, if I'm going too fast or you need time, I'm going to pause to allow you to kind of write some things down. But as I'm writing the notes, I'll be kind of showing you things and demonstrations and asking for your participation. So be ready to hit the unmute button if I'll try to call out your name and then ask a question and see if you can answer that and get you involved. And then your homework, if we have time at the end of the class, the goal will be to go through a couple of those questions together. And then your homework will be to finish those. But again, you'll find that document on Blackbaud. Okay, so is everybody ready with paper and pencil in hand? Ready to go? All right. You may even want to, I'll give you easy math that I think you can do in your head, so the calculator is not as important. All right, I'm going to switch my screen here a little bit to pin my video. All right, so yesterday, and I feel like if somebody tell me if that glare is too much on the whiteboard. So we finally have a beautiful, nice sunny day today. Hate to block the sun, but if it's keeping you from being able to see too much, or well, let me know. All right, so we ended last class on Tuesday with the concept of Newton's second law, right? So F net was equal to mass times acceleration. We have been using that equation over and over again, concentrating mainly on the types of forces and how we come up with that net force. So remember that as a net force. As I did look at everybody's homework from the lab, a lot of people answered this question based on an applied force, which was absolutely fine. The very last question asks, does an increase in the applying of force always cause an increase in acceleration? And that answer is no. It's an increase in the net force that always causes an increase in acceleration. So just because I push harder doesn't necessarily mean that it's going to move more. That depends on the mass of the object, the other forces involved, and so on. When we left last class, we ended with defining acceleration as a change in velocity over a change in time. Okay. So then we wrote Newton's second law with the definition of acceleration to say that net force is equal to mass times the quantity of change in velocity over change in time, right? And then I said, let's go ahead and multiply both sides by the delta t and get the time on the left side. So we said delta t, whoops, delta t, letter A. And I cross it out on this side, leaving us on the left side, F net times time is equal to mass times change in velocity. Okay, and that's the equation we left off with last class. So again, we're not changing Newton's law, we're just looking at it in a different way. And the purpose of looking at it in this way is it brings in our time, as we mentioned last time. So now, does it matter when I push on something if I push on it short or for a long time with that same force? And of course, as you see in this equation, it does matter. So what we want to do is define these things. In physics, the force times time is a very important concept, and so is mass times velocity. So we've given these both a separate concept of a quantity, which is that mass times velocity, we've given the quantity of momentum to, and force times time we call impulse, which is what you should have read about in chapter 5. So I just want to put those into your notes. Momentum. So lowercase p is your momentum. We're going to represent it with the P. It is a vector quantity. It is directly related to mass and velocity. Vector means it has magnitude and direction. It depends on the mass of an object and its velocity. To say that it's directly related means as mass increases, so does momentum. As velocity increases, so does momentum. Its direction is determined by the direction of velocity. So the equation to find momentum is that momentum is equal to mass times velocity. So that's your equation for momentum. Momentum is mass times velocity. So again, we took a look at Newton's second law, looking at instead of mass times acceleration, mass times, in this case, a change in velocity. So we separated and said, if I just take mass times velocity, we're going to give that the quantity of momentum. If I have a change in velocity, that's going to be a change in momentum. So we're going to come back and talk about what do these delta symbols mean. But before we do that, let's go ahead and solve for an example. What do I mean by all of this? So again, direction is determined by velocity. So whatever direction the velocity is, so is your momentum. So if something's going to the right in the positive direction, momentum would be going to the right in the positive direction. Mass is a scalar quantity and just increases or decreases our momentum. All right. So we were talking earlier about our juggling and all that kind of stuff. So I'm going to pull out our baseballs. Again, let's take a look at this baseball. If I throw it and give it a certain velocity, it will then have momentum. Sitting in my hand at rest with no velocity, it has no velocity, it has no momentum, right? So we're kind of tying all this in. Of course, for me to get it moving, I'm going to have to apply an outside unbalanced force, Newton's first law. But I can apply that force over a time period or quickly. Right? So that's why we're taking a look at this now. What effect does time have? So it has a momentum of 0 sitting in my hand. Excuse me. And then I throw it and give it a certain velocity. Let's say that its velocity now is 10 meters per second. I would estimate that the mass of a baseball is about 300 grams. So let's put some numbers to what we were just looking at here. So, for example, what is the momentum of a 300-gram baseball that has a speed of 10 meters per second? All right, Nick Land, what's our first step in problem solving?
What is the momentum of a 300-gram baseball head? I can't see the right part of, like, past of. I can't see anything.
Move your box.
Oh, right here?
Oh, Ryan's on my screen now. I can't see.
Move your box.
Oh, what?
Move the box where it shows you all the people.
I got rid of it. I still can't see.
Is it that it's not on the screen or there's glare on your screen?
Oh, I see it now. Of 10. So wouldn't you do 300 divided by 10?
Okay, wait, well, my question to you was, what is our first step when we want to solve problems?
Oh, you draw a picture of it.
Draw a quick picture. Now, this is problem number 1, so of course it's going to be our easiest problem, right? So pretty simple problem, but it's going to lead into some other stuff that we're going to do here. So in problem number 1, all right. So as we take a look at this, 300 grams, 10 meters per second, you simply have a ball, and I was right-handed, I'm favored to the right, but we could put that in there with a speed of 10 meters per second moving
What's that
to
shit?
the right. Okay, so let's say it has that velocity moving to the right. So the speed of it is 10 meters per second, but its direction is to the right. So to do a quick picture, it has a mass of 300 grams with a speed that is equal to 10 meters per second going to the right. So in our problem solvings, we draw a quick picture, right? And then next we want to, Ryan Allen, what do we do in step 2?
We have to write what we know.
Write what we know and what we want to know, and make sure the units are okay. So I kind of have mass already written here. We have velocity is 10 meters per second. I am going to write that as a velocity. I'm going to use to the right to be positive, to the left negative, as we have used all year. So I'm going to leave that as a positive number. We certainly can have things moving in the negative, and as we get into more complicated problems, that's what we will add to it. So we have a velocity of 10 meters per second, mass of 300 grams. DJ, what are the units of mass that we've been using all year?
Grams and kilograms.
Okay,
Kilogram.
grams and kilograms. In our mathematical equations, what do we typically have mass in?
Kilograms.
Kilograms. So I want to go back. I didn't list it over here, but in this equation, your mass must be in kilograms and your velocity in meters per second. Okay? So since we already knew what these variables were, I didn't redefine them. But so if we have 300 grams, DJ, I'll stick with you. 300 grams would be how many kilograms?
0.3, I believe.
Very good. So we want to move over 3 places. Excellent. So the first thing we're going to do here is change this to 0.3 kilograms.
3.
So to go from grams to kilograms, you divide by 1,000.
Momentum is 3.
So mass, velocity, in step 2, we list what we know, check our units, and write down what we want to know, right? So we're looking for momentum. Step
I've
number
got a
3,
quick-
we write our equation. There it is. So momentum is equal to mass times velocity. The mass is 0.3 kilograms, and our velocity is 10. So 0.3 times 10.
3.
That's the easy one. Hector, you do that one in your head?
It's 3.
3. Whoops, not 3 meters per second. Sorry. What are the units for momentum? Who can tell me that? I didn't write it over here. Based on mass times velocity, what are our units that we're going to have?
Is it newtons?
A kilogram meter per second squared, if we had seconds squared, would be newtons. But here we just have kilograms, meters per second. So it would be kilogram, meters per second.
It's not squared or anything. It's just kilogram meters per second.
Correct.
Alright. Let me take a picture.
Yeah, so I'll leave that up there. One thing you could do is maybe a screenshot if you want, if you are not writing that down. Okay. Okay, quick thumbs up. We all good? Not too difficult. I know you guys would find this easy. All right, so going back, the quantity of mass times velocity is momentum. It's a vector quantity that has direction. The direction is determined by its velocity. Very simple calculation of that momentum. Always making sure that your mass is in grams and your velocity is in meters per second before putting it into the equation. There's no special name for the units for momentum. It is just kilogram meters per second. All right. So that's a quick calculation. What we really want to talk about then is the process of what's happening. So now the velocity of the ball is 10 meters per second. What if I want to change it to 20 meters per second? All right. So quick calculation of that. if instead my speed is now 20 meters per second, what effect is that going to have on my momentum? John, what do you think? How much is my momentum going to be if my speed is now 20?
Whatever 20 times 0.3 is.
And what do you think it is?
Uh,
Come on, you can do that in your head. What's 2 times 3?
6.
6. Because the 0 puts the decimal over, right? So we
Yep.
get 6. All right, so let's say I take a ball and I throw it from 10 meters per second to 20 meters per second, right? So now we have, if I could ask what is the change in momentum for a baseball that goes from 10 meters per second to 20 meters per second to the right. So we're not going to change its direction. We're not going to allow that direction to change. We are simply going to go from 10 meters per second to sometime later 20 meters per second. Right?
That's what I was thinking.
Right. The mass is still going to be 300 grams, 0.3 kilograms. So here we found its momentum. In this position, we'll call this position 1, or we could call that our initial position. That's what would be a better word. And this is our final position. So the initial momentum, we already found to be 3, right? 10 times 0.3 would be 3 kilogram meters per second. Over here, our final momentum on this side is equal to the same thing, mass times velocity in this position. So that would be the 0.3 kilograms times a velocity of 20 meters per second to give us a final momentum of 6 kilogram meters per second. Okay. Good morning, Tucker. You keep sleeping in on us. Good morning.
Morning.
How are you?
Good.
Good. All right. Missed some notes here at the beginning, so you can go back and watch the video or get those notes from one of your classmates. But we're talking about momentum. So the concept here is now I have momentum here. If I throw a ball and it gets faster, I have more momentum. Specifically, if I doubled my speed, I doubled my momentum, right? So that's what I meant in the beginning on the definition of that momentum and velocity are directly related. Okay, so momentum and velocity are directly related. So if you double speed, you will double the momentum. If you half it, you will half as much. So I want to go back to that original equation where we had F delta T. So I'm going to get rid of this sign. Okay. Whenever we have the delta in there, Matthew, do you remember what the delta means?
It's the change in.
The
Some-
change in.
Yeah.
Mathematically, it always meant final minus initial, right? So it was the change in or final minus initial. So what we have over here is force times a delta t, the change in time. And we typically take the initial time to always be 0. You start your clock whenever you want, and you're looking at the movement of something. So we typically always have that as being 0. So this side of the equation typically becomes just force times time, okay? Now, if an object is moving, for the most part, its mass isn't going to change. Something like a rocket where it loses a lot of gas as it's moving everything, its mass is definitely changing. And if you have a collision and things stuck together, their mass might change. But over here, putting in this delta symbol and the quantity of mass times v, I can pull out that delta symbol and say it's really a change in the quantity of mass times velocity. This quantity is momentum, so I can replace that with momentum. So what we're really saying here is force times time equals a change in momentum. So this side, this is your change in momentum. Okay. Which is what we just found over here. So to find that, you typically are looking at a change in velocity. Okay. So we have initial, final, mass. So in this case, our change in momentum would be our final momentum minus our initial momentum. But I found my momentum by taking mass times velocity. So to answer the question, what is the change in momentum of a baseball that goes from 10 to 20 to the right? My change in momentum would be my final momentum minus my initial momentum, considering direction too. So this would be 6 kilogram meters per second minus 3 kilogram meters per second. My change in momentum is 3 kilogram meters per second. Nick, probably can't see that. There we go. All right, I'm going to pause and let you all kind of write that down. Okay, you guys are all unmuted. So just real quick, any questions on all of this?
Friday.
What'd you say, John? Nick?
I thought today was boot camp Friday.
Today was Boot Camp Friday. Did you come prepared to juggle?
Well, no, I thought we have a new boot camp Friday.
Oh, you're right, because it is the first of the end of the week. But remember, if you remember last week, I had done a Boot Camp Friday last Friday because it was a Friday. Not sure what this week would bring. But no, sorry, you got to get your brain wrapped around it today.
Okay.
And but it is relevant to our Boot Camp Friday because I'm going to tie back in our juggling here at the end. So last week's Boot Camp Friday is not due until next Friday. So you guys have all next week to practice your juggling if you haven't started yet. We'll talk about that at the end. But yeah, this is a little maybe a little heavy if you came in thinking you were going to have a Boot Camp Friday. Sorry, Nick. All right, anybody else? Good?
Just right.
Yes, Ryan.
We're gonna ever use this to find acceleration also?
Say that again. Are we ever going
Are we
to?
gonna have to find acceleration out of this?
We could. So I keep going back to the original equation so you can kind of see how it's all tied together. If I gave you an acceleration, you could turn that into a change in velocity over change in time. So, as you get into more advanced problems, that's what ends up happening. Like all of this gets tied together. And that's why I've been stressing all year about the good problem solving skills. What do you know and what do you want to know? Because now we have lots of equations that contain the same variables like mass, force, acceleration, right? All of our motion equations and stuff. So I really could give you a really challenging problem where we go back to motion and a car is moving and then how fast is it going at the end given that acceleration and so on and so on, which I know you guys could do, and that's the goal. That's what we eventually will hopefully get to, okay? All right, so getting back to this, I will change the momentum of a baseball if it starts with 10 meters per second and now it's going 20 meters per second. It's just not going to happen on its own. You are going to need an outside force, right? So if I want to change the momentum of something, and the reason, you guys have used the word momentum many of times. It has momentum. Oh, we need more momentum to get going. It's in every coach's speech out there about having more momentum, right? Well, momentum is the concept of energy, which we'll get to next. It's a concept of motion. It's a concept of doing something. So here we have the baseball go from 10 to 20, increasing its momentum by value of 3. So on the right-hand side of this equation, I would have a 3. That's how much I changed my momentum. So if I wanted to go from here to here and change by a value of 3, I have a choice on how I'm going to do that. We already know you're going to have to apply a force. But now we recognize I can apply a force over time. And this is the major concept for today. Time now comes in there. All right, so let me get rid of the left side. Is everybody good on this side?
Yep.
All right, so let's talk about time. What do we call this quantity? Okay, this side of the equation is called an impulse. Okay, impulse. Okay, an impulse causes a change in momentum. Impulse, given a capital J, is force times time. It is also a vector quantity, so you apply an impulse over the time period. Okay. Its units are Newton seconds, so a unit of a Newton times a second. So nothing has changed, all of this. For the most part, we look at it as just force times time. We can give it its own letter of a J if we're just solving for impulse. So if I want to change an object's momentum, I can apply a big force over a little time, or I can apply a little force over a big time, right? Both of those would cause the same change in momentum of an object. So let's go back to our baseball scenario, right? I guess I should have kept that equation up there. Yeah, force times time is going to cause our change in momentum. On the right side, we have a 3 kilogram meters per second, which is a Newton times a second. So if I'm strong enough, I can apply a force of 3 newtons. How many seconds would I have to apply that force to get 3?
1.
Times 3 gives me 3. That's an easy one. So I'll give that one to, who wants that one? Chase? What times 3 gives me 3?
1.
1. Very good. So I can apply a very strong force over a quick 1 second and make it move, right? to get it to a change of velocity of 10 to 20, causing a change in momentum of 3. But let's say I'm not so strong. What's my other option? Roth, what do you think? If I'm not very strong, but I still need this to be 3, I still need that side to be 3. Over there, I applied a big force over a short time. What other 2 numbers could I multiply together to give me 3?
1 and 3.
1 and 3.
1 and 3. I could make this number 1 Newton times 3 seconds, and I'd still end up with the same change in momentum.
Yep.
Does that make sense?
Yes, ma'am.
Okay, so for everybody, let's just reiterate what we're saying here. And this could be for anything. It could be a car, whatever you're changing the momentum of. If I need to change its momentum, I have to apply a force. Now we are saying, what happens with you applying force through time? So I can change this object's momentum by a quick force, but that force is going to have to be big. I can change the momentum by applying a small force over a long time. I don't need as much force. I use time as a way of making that momentum change instead. So all of you athletes, right? When you throw a ball, when you hit a ball, when you kick a ball, right? What do we call this, Ryan, in baseball? If your coach says you need to, what's that?
Is that swing?
Follow
No,
through.
no, what do we call this in your swing? This part of your
Yeah,
swing is
follow
called the,
No swing.
Tucker, shut up.
maybe I'm not explaining it correctly.
Oh, that's
I
good. Yeah,
hit like this, but I really need to hit like this. What's that called?
follow through the ball. Follow through the
Follow
ball.
through. I have to
I
follow.
said that. Okay.
When I was coaching my volleyball girls, right?
And a baby Nick.
No, you didn't. You're.
Let's get the better sport out.
No.
Let's forget baseball. Let's get to the good sport.
Yeah.
Volleyball, right? When I was teaching my girls to hit the ball, when they would spike it, they wouldn't want to just tap it like that. That's a hard force over a quick time period. But sometimes I'm only so strong, so I can't change this force. My other choice is to, when I really hit, to follow through and keep my hand in contact with that ball. And that follow through, right, as you swing your arm or anything, gives you more time in contact with the ball to cause the same change in momentum. Does that make sense? Thumbs up? Okay. But it goes the opposite direction too, right? So there might be times when, if I want to change my momentum, instead of me, if I want to catch it, right? So you have a choice of a big force, short time, small force, long time. All right, so let's all kind of practice this. You all look a little sleepy. Everybody stand up. I don't need to see you, just listen to me. All right, if you want to jump, so the other side of volleyball is you have to be able to jump into the air. What do you do to get up as high as you can?
Jump off 2 feet.
What do you do with your legs? Do you keep them straight and just push off like that?
You bend them.
You have to bend
Bend.
your legs and jump up high, right? What are you doing when you bend your legs, John? In terms of impulse. John, what am I doing when I jump and I bend my legs?
You're pushing force off the ground.
Correct? With
Pushing off the ground.
which one of these scenarios? More time or less time?
Less time.
Less time.
When I jump,
More time. More time.
the purpose of bending my legs, if I bend, I'm pushing on the floor the whole time I'm straightening my legs. So my feet on the floor are they're only so strong. But I can jump higher if I extend the time in which I push on the floor. So I will go higher. Now the opposite is true too. when I go to land, everybody stand up one more time. This will really wake you up. You are to jump as high as you can, but when you land, don't bend your knees.
That's what hurt.
I hope somebody breaks their leg.
Roth, what did that feel like?
You gonna break
Nick,
your
you
leg.
still have your pajama pants on.
Oh, I rolled my ankle.
That's what you
All right,
do.
Ryan, what did that feel like? You said right away that's
hurt.
going to,
Yes, it hurt. I
it's
bet
going to
it.
hurt.
Yeah.
All right, now why does that hurt?
Jumped.
Because you're not absorbing. No, you're just falling. Well, yeah, but then you're falling in a less amount of time, right? Or no?
Less
No.
time.
No,
Okay, I liked your word that you used about absorption. You're not absorbing the force. So what does that mean about absorbing? Now in physics, we say you are not applying a long time through a small force. No matter what, you have to stop. So your momentum is going to change. You're coming down with a certain velocity and then you're going to stop. So you have to change that object's momentum, which is you, by applying an impulse. So going back to this, I'm going to stop. So I had a speed and then I have to stop. So I have to apply an impulse. That impulse is a combination of force times time. So by bending your knees when you land, you apply an impulse with long time, little force. Okay? All right, one more question here. Let's see how much time we got. We got plenty of time. All right, let's go back to this scenario. If I want to catch the ball, right? So going back to baseball, Tucker, when you catch a ball, what do? So the ball is coming in, it has, in all of our physics term, a ball moving has what?
Acceleration, velocity. I don't know.
Has both of those. And therefore it has, you weren't here at the beginning of class. Garrett, what does that have as it comes in? If anything that has velocity has, our new word for today.
Acceleration.
Momentum.
Momentum. It has
Yeah.
momentum. So if it has momentum and my job is to stop it, then I'm going to cause a change in momentum, right?
Mhm.
In order to cause a change in momentum, I have to apply an impulse. That impulse is a force over time. So, Tucker, when you catch the ball, what do? This ball is coming in very fast. It has a high momentum, and I'm going to stop it. What am I going to do to stop it so that I don't break my hand?
Oh, I just catch it. I didn't really like pull my hand
Wear a
back.
glove.
Yeah.
Number one, you wear a glove. And what does the glove have in the
net.
hand?
A web.
There's some padding there, right?
Leather.
A little bit, leather glove. So that's providing a little bit of padding. So that allows there to be a longer force. You pull back a little bit, okay? Your arm probably goes back some to absorb all of that, right? All right, so let me pull up your, let's see if I can pull up your homework. How much time? We only have a few more minutes left. All right, so for your homework, you have conceptual questions on Blackboard that you will pull that up. You do not have to print it out. So a couple things I want to say about your homework. I know you guys, you're running your printers ragged and everything like that. So as you are taking a look at your homework, if you don't want to print it, it's in a Word format too, so you can type into it and send that back, or you can print it, write on it, or you can just write your answers on notebook paper, okay? But you will see in today's homework a little bit of extra credit. Looks like we might be in for a nice weekend. One of my favorite things to do when we celebrate Easter, which might be a little more challenging this year, is we always have a nice egg toss, raw egg toss, or a water balloon toss. All right, so this is always my favorite, because if we were at school, we'd be going out and having a water balloon toss. So your extra credit is to answer the question, first of all, what's the key in winning the water balloon toss?
Oh, I know.
Follow it back
Right.
so it doesn't.
Yeah, when you catch it, you have to like bring it.
Yeah,
Okay,
yeah.
so now, everybody,
be
my
one-
physicists, my future engineers, let's use our physics terms to explain what you're doing when you catch the ball like that. Ryan, use everything
would
we
that be
learned
con-
today to explain
Would
that.
that be considered an impulse? So like when the momentum comes, you have to, like hold your hand and that would cause an impulse. So like stop the momentum of it, but then you have to. Oh, that would also be the force of force and time, right?
Correct. You're exactly right. So you have to stop its momentum. You have to change its momentum to be 0 because it's going to have momentum. You have to change it to be 0. I have to apply an impulse. So by doing this, I am increasing time with less force, right? If I catch it abruptly and quickly, like I run after it to go catch it and I catch it, now I'm going to have to apply the force over a short period of time, which means it's going to be a high force hitting this, so it's going to break, right? So a force might cause this to break, but if I apply a small force over, or down here, small force over a long time, then it won't break, and I can catch it like that. All right, so next week, you might owe me a few videos. One, if you want the extra credit, and remember social distancing, 6 feet. Take this all serious, you guys. We're in the middle of quite a crisis, but I think we're getting a good handle on it. 6 feet apart, just your family members. Don't be calling each other up to come and play. But go outside, make a water balloon or an egg, have an egg toss. I'm going to see how far apart you can go, and I want to see you proving to me how you're catching this in terms of small force, long time.
Wait, when is that due?
Not till next week. So, well, the video, if you do it, it's over this weekend. So your homework is due Monday. The video for the boot camp Friday of juggling is not due until next Thursday, I guess, since I don't have you on Friday. So did I explain to you how this is going to work? You will send me a video on the juggling. I will time everybody. I will total your time for the class and divide by how many kids are in the class. And then that's your time. I will tell you right now, C period is definitely winning. They have, although Chase said he's going to do 4, they have one person doing 4 and one person doing 3 very, very well. So I don't know if I can concentrate. I'm getting better. All right, gentlemen, any questions?
No.
No.
Wait, the
Hector.
balloon thing, like somebody could easily just paint like a balloon or paint like a baseball. And
I think I can tell in the video.
I don't know.
You can have fun. Have fun with it. Now, if we were, I mean, it is always my fun activity to do. So, all right, gentlemen, you don't have to by any means. It's just thought of something fun. DJ, you doing all right?
Yes.
Looking tired? Joseph, I can't see you. I hope you're doing okay.
I'm doing
And
all right.
I guess it's lunchtime, gentlemen. So,
Somebody send me the notes.
I got you, Tucker. I sent them already.
that was very nice. All right, Nick, hope you enjoy your show you've been watching there the whole time. What are you watching?
Nothing.
Nothing.
Okay.
All right,
I've
gentlemen.
The notes though, I have everything.
Anybody's welcome to stay behind if you have any particular questions. I will be back on at 2 o'clock for office hours if anybody needs anything.
Okay.
Bye, Ryan. You guys have a great weekend. Stay safe and healthy.
You too.
Bye, Garrett.
So we got to do the momentum questions in the class documents.
Correct. Did you see it?
Yes. When is it due? I'm sorry.
That is due for you guys, I'm sorry, on Tuesday.
Okay.
So
Thank
you guys, next time we have classes when it's due. So for you guys, that would be Tuesday.
Ones walk
All
through
right.
those questions.
Just those questions, yes.
All right.
All right.
Okay.
Thank you.
You're welcome.
Have a nice weekend. Bye.
You too. Thank you.